Okay, so good morning, everybody. I'm very happy to have a research seminar by Professor Rose Yu from the UCSD. So I want to briefly introduce her. Dr. Rose Yu is an assistant professor at the University of California, San Diego. She was a postdoctoral fellow at the Caltech, and her research focused on advancing machine learning technologies for large-scale spatial-temporal data analysis with application to sustainability, health, and physical sciences. A particular emphasis on her research is on physics-guided AI, which aims to integrate first principled with data-driven models. So she has won faculty research awards from Google, Amazon, and Adobe, several best paper awards. Oh, this is really great. And best dissertation award from USC, and was nominated as one of the MIT Rising Stars in EECS. So therefore she's a very young, good talent. So I'm very excited to have you here. So please welcome to the Professor Rose Yu. So please start.
Thank you, Makoto, for the nice introduction. Yeah, Makoto, they invited me to visit Riken a couple of years back, and I had a wonderful experience there. So today I'm happy to share some of the recent research from our group. And this is the logo of our group. So it looks like a rose because I go by Rose, but it actually has the letter S and T in it. Stands for Spatial Temporal Machine Learning, and that's our research focus. I also want to mention that our lab is relatively new to UCSD, so we're always looking for talented students, like graduate students, postdocs, or even visitors. Please let me know if you have ever interested in visiting our lab at UCSD. And I think let me start with a few examples. And this is a video showing the progression of pandemic for past year. And you can see, pandemic is getting, it has affected our life significantly. And that's precisely why I cannot visit you guys in person. So if we can forecast the number of deaths and hospitalization, then we will be able to inform public health experts in decision making. And I also heard about the Olympics happening in Japan. So since we're all actively working on this area, if you're aware of any data sets or intriguing problems, please let us know as well. So in epidemic modeling, as you can see, it's an intrinsic spatial temporal problem because the number of cases over different days is changing rapidly. And then the different states or different locations are highly correlated because travel. So traditional mechanistic models such as SIR models often require rigid assumptions of underlying dynamics, and they often assumes full observability, meaning they need a lot of data points seen at different compartments in the SIR model. So here, nowadays we have access to more data collected by contact tracing. Right? The question is, can we utilize this high resolution space-time data to better model the pandemic and forecast disease progression? The second example is in the field of climate science. So climate science are built on the climate models. The climate models are a suite of partial differential equations that govern the evolution of atmospheric dynamics. However, climate models are very slow to simulate. At high resolution, running one simulation model across the globe usually takes a couple months. Now, with access to real-world data collected at different stations, the question is, can we learn from this type of model, learn from this kind of model as well as the data so that we can build surrogate models to speed up the simulation for climate modeling? The next example is in the field of traffic modeling or transportation. So this video shows the progression of traffic flow in one day in the city of Los Angeles. And the bubbles represent accidents happening from morning to night. So transportation research has traditionally relied on mechanistic models to capture drivers' behavior. But these models are very rigid and not consistent with real-world traffic patterns. So again, we have access to a large amount of sensing data collected at high frequency. The question is, can we leverage this data to improve the trajectory planning and traffic control? As you probably have guessed it by now, from different examples in climate public health, climate science, and transportation, and even generalized to many other fields in science and engineering. The common pattern is that the data generated from these fields contain very rich space and time information. So if we can accurately learn the underlying spatial temporal dynamics, we will be able to better predict the future in real time and make important decisions. Now, the research aim that we recently focused on is physics-guided learning. So physics, in fact, is a discipline that has been studying spatial temporal pattern for decades. So physics rely on first principle models to derive model-based approaches. And in physics, there are a lot of tools that scientists have developed over the past few years to describe the space-time evolution. For instance, there's tensor network, which is I studied for my PhD thesis. There are differential equations, which governs the underlying system. And there's symmetry that is intrinsic to different physical properties. Physics-based models rely on first principle modeling, and therefore they naturally encode domain knowledge. So they're very sample efficient, meaning they can learn with very few data points. However, physics-based approaches are often computationally expensive, and they often suffer from model misspecification problem, means that the rigid assumptions underlying this model can be very far away from real-world data. On the other hand, in machine learning, we often perform statistical inference and use data-driven approaches. So in machine learning, we also have our own tools, such as graphical models, deep learning or neural network, and variational Bayes, which is a type of Monte Carlo inference method, Monte Carlo sampling methods. Machine learning methods are computationally efficient, and because they are data-driven, therefore they are more realistic than first principle physics-based models. However, often also because they're data-driven, they require a lot of data to learn. For instance, the very famous example of AlphaGo, which is the computer game that beat the professional Go player, requires millions of data points to train, which is not practical for real-world applications. On top of that, machine learning models are often assumed to be black box models. They're very difficult to understand or even generate physically meaningful predictions. So the goal behind physics-guided learning is essentially combining the best of both approaches, where we wanted to integrate physics-based principles and domain knowledge into data-driven machine learning models. In this way, we can encode inductive biases, we can improve generalization to unseen test distributions, and we can reduce sample complexity of the learning algorithms. Most importantly, we can increase our trust in artificial intelligence because the models we build are better interpretable, and they are also relevant to domain science. Okay, so within this broader paradigm, we have developed different techniques to integrate physics and machine learning. And today's talk, I wanted to give a few examples to show you various ways that we can integrate domain knowledge and physics principles to model complex spatial temporal dynamics. By the way, feel free to interrupt me if you have any questions. The first idea is called residual learning. This is actually a very simple idea. Consider the case where we have input time series x1 to xt. So x1 can be a high-dimensional vector, and this represents the system evolving from time t from time 1 to time t. The goal of learning dynamics is essentially learning a function f, which is to approximate the underlying equation that governs the time series. So essentially, we want to learn a function f that can give us accurate forecast. In this case, this function will take the historical states x0 to xt as input and hopefully generate accurate forecasts which give us precise estimates of future states xt plus 1 up to xt plus h. And here, the capital H stands for the forecasting horizon. And in residual learning, what we assume is that we have access to some physics-based models, and these can be easily derived from first principles. However, often these first principle models are not perfect due to partial observability and noise in the data. So the idea of residual learning is essentially learning the correction term of the physics-based model. So we can write out the function f as a composition of two functions. G represents the physics-based model which we can use from any partial differential equation of first principle models. And R represents the residual function. And instead of learning the original dynamics, we're going to learn this residual term. Essentially, this residual term is a correction to the physics-based model from real data. So let me show you an example of how we can achieve this. Even with a simple idea, there's still some intricacy of how we can make it work for complex dynamics. The application example I want to talk about is a phenomenon in aerospace engineering, and this is called the ground effect. So if you ever played with drones, you might have noticed that the drones are rarely easy to control when it flies in a normal wind condition. However, when you fly the drone closer to the ground or trying to land the drone on the surface, the drone will really start to wobble a lot. This is because if you look at the picture on the right-hand side, there is air being generated from the two rotors of the drone. And this air will interact with the ground, which creates turbulence. So this turbulence becomes very significant to the drone because it's rather lightweight. And this will create instability and sometimes even cause the drone to crash. So because we cannot accurately model the effect of turbulence, because turbulence are very difficult to simulate even in simulation, it's impossible to provide an equation for the so-called ground effect. And therefore, this is an open question in the control and aerospace engineering community to how to land the drone stably onto the surface when there is the air turbulence that disturbs the drone. So in this paper, which is published in ICRA 2019, we provide a hybrid solution that learns the correction term of this air turbulence. This hybrid framework is essentially built on top of a physics-based model. So in this mini example on the left-hand side, we have a physics-based model to describe the motion of the drone. The gray box is the body of the drone. It has two rotors, the green and the pink one that generate thrust that lift the drone. The drone also has its own body weight and the air drag, which drags it back from the forwarding direction. So we can define the position of the drone P, velocity V, angular velocity of omega as the state of the system, which we call as a T minus 1. And then all the variables in black are observed variables, which we can measure using sensors on the drone. These include the state of the system, the total thrust and torque, F and tau. But the variables in red, which are unknown disturbance force and disturbance torque, these are created by the air turbulence. We cannot measure or accurately calculate. And these are the unknown terms in the physics-based model. So let's look at the one-step loop in this control pipeline. We have the state of the system as T minus 1, which include the position, velocity, and angular velocity of the drone. We have the control from the previous timestamp, which basically changed the speed and the direction of the drone. And then we pass this input into a set of differential equations. These are the physics-based model for the motion of the drone. They're easily derived from Newton's law of physics. As you can see here, all the variables in black are observed or can be calculated. However, the air turbulence, disturbance force, and torque, which are the terms in red here, are unknown or not possible to be calculated. So we want to learn the residual terms, which are in red. The very first idea of residual learning is just to approximate these residual terms with the deep neural network. And then perhaps we can generate a next estimate of the states, which give us st plus 1, st, and we repeat this loop to control the drone. Okay, so the first idea we came up with is to learn the residual term, which is this f of a, and we approximate this term with a deep neural network. However, when we started doing this, we almost crashed the drone. So the simple idea didn't work in the beginning. When we investigate this issue, we realized that in learning dynamics, by simply approximating this residual term with the deep neural network is not enough. Because the deep neural network is very flexible, so the learned dynamics can be too flexible. And in the dynamics learning context, if the dynamics is too flexible, that means the control is not going to be stable. So if the control is not stable, the drone will easily crash and getting out of control. So that's why simply using a deep neural network to approximate the residual is not enough. What we ended up with is a technique called spectral normalization. And this is a way to regularize the learning behavior of the deep neural network for this residual term, and it allows us to learn the stable dynamics. So spectral normalization is not our invention, obviously. It's just a way to constrain the Lipschitz constant of a deep neural network. Let's consider the deep neural network as a multi-function composition. Let's say I have a function f, which is a composition of functions g. Each g function is representing a function in a layer. So if we have L layers of neural network, we have L functions composing with each other. And the input of the previous layer is fed as the output of the previous layer is fed as the input of the next layer. So every layer, G of X, is basically a weight matrix W times the input X applied by a nonlinear activation function phi. The Lipschitz constant of a function is essentially the largest of the slope. On the picture on the picture on the right-hand side, we're showing you a function f of z, and the Lipschitz constant of this function is essentially the upper bound of the slope alpha, tangent alpha. As you can see here, if we can bound the Lipschitz constant of this function, we are essentially regularized how much or how wide the output of a neural network can be. And in this way, we can guarantee that the learned dynamics is stable. So for a deep neural network, unfortunately, we cannot compute the Lipschitz constant exactly, but only approximately. So we can approximate the Lipschitz constant simply by the product of the largest singular value of each layer's weights. So WL is the weight of every layer, and sigma of WL is the largest singular value of that matrix. If we multiply all the singular values together, it gives us a rough upper bound of the Lipschitz constant for this deep neural network function. So if we want to regularize the Lipschitz constant, what we're essentially doing is to basically divide the weights by these largest singular values. And this happens during training. So when we train this neural network with the drone data, we can basically regularize the weights by dividing it with the largest singular value of itself. Of course, computing the singular value it might be computationally expensive, so we actually didn't do this for every iteration, but rather a few iterations. Okay, let me show you the results, right, when we apply this type of hybrid framework to drone control. We compared with a state-of-art controller based on PD control, and that controller does not have the learned turbulence term in the model. Where our hybrid model learns the air turbulence term, which now enables stable control. So what I want to show you here is the task of tracking flying around the table. The top one is our method, which we call neural lander, and the bottom one is the baseline. Because our model is learning the turbulence term in the model, it enables the drone to fly closer to the table without crashing. Where the bottom model basically has to fly very high up on the ground to avoid crashing. And this is particularly useful for disaster rescue case when we want to fly a drone closer into the tunnel. Let's also look at the effect of the spectral normalization. The left one basically shows the task of landing a drone onto the ground. And the left one is with spectral normalization. The left one is without. This shows the heat map of vertical distance over vertical velocity. What we can see is that the trend of velocity distance, vertical distance and velocity extend from training set to the new set. And it shows that the model with spectral normalization generalized much better. The right picture shows the same effect for the previous task I showed you of flying around the table. With spectral normalization, the model learns the heat map of the table, even though we do not tell it the boundary of the table. However, without spectral normalization, the model doesn't learn about the table shape, and therefore it doesn't generalize. So interestingly, Peter Barley's paper characterized the generalization bound of spectral normalized DNNs. And in machine learning, stability is actually an indication of generalization. So what we showed in our paper is that by applying the same technique of spectral normalization to learning dynamics, we are actually allowing the deep neural nets to generalize better to a different on-sync distribution. Okay, so that's basically the first part of how we can learn the residual terms of a physics-based model. Let me just pause for a few seconds and see whether there are any questions.
I have one question.
Sure.
Just a second. So actually, this is really nice results. And what happens if you change the environment? So this is currently you train the model with the table on the bottom, right? But if you change the environment, is your algorithm still can somehow generalize to that environment as well?
Yeah, that's a great question. So in this case, right, the table, even though it is the same table, we're actually flying a drone only on a subset of regions. So the generalization right now is in distribution, right? So the question of out of distribution generalization is much harder. So we actually were testing, generalization of this algorithm to wind tunnel, right? So the drone we're flying in a very different wind condition. It's still a work in ongoing. But that's a great question. And in terms of the generalization bound, I think there is also a limit to which this algorithm can generalize.
Thanks.
Sure. Okay, then let me talk about a second example of how we can integrate physics principles into deep learning. Right. And this method, let's see, does DNN have a special architecture? Actually not. So the DNN turned out to be very simple. It's just a multi-layer perceptron. When we train it, we use spectral normalization. The reason we make the DNN very simple is that we wanted to deploy it on the embedded system on the drone. So we actually don't want complex deep neural networks because that might cost more energy. But that's a very good question. Okay, so then let me talk about the second example of integrating physics ideas into deep learning. And this is called the trainable operator. So again, we're in the same setting here. We have the input time series, x1 to xt, right? x1 is representing the state of system at time 1. And we have basically the state of system for a sequence of states from the system. So we still wanted to learn the dynamics, right? Which we wanted to learn an underlying function that give us a mapping from previous states to the future. So here I make it more general, and saying that I want to learn this function f, then map the input states x of t into output states y of t, and y of t can naturally be the next state, which is xt plus 1, and that's the forecasting setup. So the difference of this one, this approach from the previous one is that we assume the f to have certain structure, so that it is actually a mathematical operator that we can derive. For instance, this operator that you might be familiar with, this is called the Laplacian operator, right? Essentially, it convolves along this function f of t using an operator e to the power of minus x of t. And this Laplacian operator is calculating a convoluted version using a filter, right, to change the format of this function. And naturally, if we wanted to calculation of this operator, we need to perform numerical integration. The key idea behind the trainable operator is that we actually do not need to compute the numerical integration in this case, but rather we're going to parameterize this function with the deep neural network, and then we're going to make this function as a trainable weights in the mathematical operator, and this operator then becomes a convolutional neural network. And that's kind of the idea behind trainable operators, because the convolutional neural network essentially is the discretized version of a convolutional operator. So this idea of trainable operator generalizes the simple ideas behind convolutional neural nets. Okay, then let me talk about this idea in the context of COVID-19 forecasting. Right, as I mentioned before, we're very interested in this problem, partially because it's a natural spatial temporal problem, and also because the urgency of this problem. So we are part of the official team of United States Center for Disease Control and Forecasting. So this is our team. UCSD and UU team, because I actually belong to two schools. I transferred from NEU to UCSD, so I have two affiliations. And we are part of the national forecast, where we send forecasting results to CDC every week. And this work is a joint work with my students, Alan Wu, and our collaborators at Northeastern. So let's just formulate the problem of long-term forecasting again. Let's say I have a system with a state f of xt, and the system is governed by some parameters phi. So a dynamical system can be written as a set of differential equations, Ci, and Ci takes the input x of t and different orders of derivative of the system. So dxt is the first order derivative that represents the velocity, right, in a context of physical systems. And there's a velocity, acceleration, etc. So a dynamical system can always be written as in this format, and possibly with some stochasticity. Now, learning a dynamics model for long-term forecasting is to learn a function that maps from the historical states x0 to xt into the future states xt plus 1 to xt plus h. Now, the difficult part is that we not only want to do forecasts, but we want to do spatial temporal forecasts. Right? In this case, we need to capture both the spatial and temporal dependencies. So in the context of COVID-19, we need to consider the travel patterns between different locations. And these basically correlates the number of infections at different places. And of course, there's a temporal dependency, and this shows basically the number of cases over time. You can see that clearly it's not a stationary dynamics because they're bursts due to like sudden changes of weather, or even a major change of nature in the virus. Okay, so then how can we learn the spatial dependency? Well, in this case, we borrow the idea from convolutional neural nets, right? So in convolutional neural nets, it designs a local structure for spatial data. So for image data, it views the image as a regular grid, and it uses convolution to model the local spatial structure. So for pandemic, the spatial structure is not on the grid. So essentially, the idea behind spatial modeling in this paper is that we think the pandemic spatial dependency as a graph. So it's a regular graph where the nodes represent different states and the edges represent the travel behavior. So we leverage the previous work of ours to derive convolutional operation to directed graphs. And this leads to the convolutional diffusion convolution because we think the pandemic as a diffusion process. This idea actually came out of our previous paper at Unclear about the traffic forecasting. So the diffusion convolutional neural network itself was derived from the previous paper, which models the dynamics, the diffusion dynamics on the graph. Right? So let's say we have the adjacency matrix Aij, and each element in this adjacency matrix is a distance measure. So it basically tells us how close two locations are in terms of travel. And then with the adjacency matrix, we have defined the in-degree and out-degree matrix. And these are the row sum and the column sum of the adjacency matrix. So our results leverage this theoretical results from graph theory and 2016, which characterize the stationary distribution of the diffusion process. This says that the stationary distribution of a diffusion process is essentially a weighted infinite weighted sum, right? Where we sum over the inverse of the degree matrix multiplied by the adjacency matrix. So D inverse times A itself is called the random walk matrix. And when we raise this random walk matrix to different powers, it represents different degrees of random walk. For example, random walking to the first neighbor, second neighbors, and etc. And the theta parameters are representing the diffusion speed at different steps. So this equation is essentially a discretized representation of the so-called diffusion operator on the graphs. So that basically comes back to our first ideas, second ideas of mathematical operators. So this diffusion operator itself is a mathematical operator. So we can basically replace the weights or the coefficients in this mathematical operator with trainable weights in the deep neural network. And that leads to our diffusion convolutional neural network. And in this case, we have the diffusion convolution, which we represent as star G, where G represents the graph. And taking the state of the system, xt, we have the weights of the neural network. So we have theta O and theta in. And these are the in-degree and out-degree diffusion, which are the parameters in our neural network. So we have D inverse A, which for both the out-degree diffusion and the in-degree diffusion to capture bidirectional diffusion in a pandemic. And xt is essentially the input, and these are the concatenation of number of deaths for all the states. So if we have 50 states in the United States, and xt is a 50-dimensional vector, depending on how many features we want to predict. For example, if we want to predict the joint set of number of deaths or number of infections, and that will grow, right? So if we have 2-dimensional feature with 50 states, that will become 100-dimensional vector for xt. So we can integrate this equation into any recurrent neural network. For example, as a sequence-to-sequence model to forecast the dynamics of the spatial temporal pattern for the COVID-19. And we will not go into details of how we can integrate this component of the diffusion convolution into recurrent neural network, because rather standard, we can basically replace the convolutional RNN with diffusion convolutional RNN. That will allow us to predict multivariate time series with spatial structure. But what I want to talk about is for the pandemic, just predicting the number of cases or number of deaths is not enough, because in a very limited sample regime where so much uncertainty going on in the pandemic, generating deterministic forecasts is not enough. Most importantly, we want to provide the uncertainty or probabilistic forecast with deep learning. So this new paper that we just published at KDD in 2021 gives a partial solution to how we can generate forecasts with uncertainty in deep learning for spatial temporal forecasting problem. So in this paper, we investigated 6 different uncertainty quantification metrics in deep learning. We categorize them to two classes, the frequentist approach and Bayesian approach. One example of frequentist approach is quantile regression. So quantile regression basically is to replace the loss that you typically use for forecasting, such as mean square error or mean absolute root mean square error, with a different loss function. And this loss function is called the quantile loss. So essentially, if I have the prediction y hat and the ground truth y, the quantile regression loss will calculate this pinball loss function, which essentially is a step function depending on whether the difference between the ground truth and the prediction is larger than this quantile tau. So tau is the confidence interval, and if we set the confidence interval tau, we will have a different loss for this particular quantile, and that will automatically generate the interval that we want in probabilistic forecast. So this is one of the examples for frequentist approach. And for Bayesian approach, we looked at a type of algorithm called stochastic gradient MCMC. So stochastic gradient MCMC is a faster way to basically sample from the posterior of a Markov chain for a probabilistic model. So this algorithm stands for stochastic gradient Monte Carlo, Markov chain Monte Carlo. Right? The high-level idea is that when we train a deep learning model, we often use stochastic gradient descent, which is in this format if we have the weights of the deep neural network written as WK at case iteration, right? And then the next iteration, WK will be the W minus the stochastic gradient. And eta here is the step size, and I have a tilde here because delta of L will allow the loss function of this weights is only approximate because we're not calculating the gradient with respect to the whole data set, but rather a small mini batch of data set, and that's the idea behind stochastic gradient. But the idea behind stochastic gradient MCMC is that we need to inject the noise, which is P of K, at every iteration following a Langevin dynamics. And if we actually inject noise in this way, there's a result that can show when it converges, this chain, Markov chain converges, it actually gives perfect example of the posterior for the deep learning. So this is the idea behind Bayesian method for quantifying uncertainty in deep learning. And obviously, SGMCMC is quite computationally expensive because we have to run multiple chains at the same time, right? So collecting examples from the posterior is not very efficient, but it does give very good uncertainty quantification. I also want to highlight that in UQ, it also matters what kind of metrics we wanted to measure because point estimation is not enough. But then often the common metric is to evaluate holdout likelihood, but for deep learning models, it's impossible to write out the log likelihood for a deep learning model. So what we opt for is a surrogate, which we call the mean interval score. So this mean interval score is an interval score based function. And it basically asks the deep neural network for 3 things. The deep neural network will generate the upper bound and the lower bound L, the upper bound U, the lower bound L, and then the prediction Z. So for the 3 triplets, we're going to plug this into this mean interval score. It basically tells us how well this prediction falls between the upper and lower bound, and that basically means the coverage, as well as the size of the interval, which is basically tells us how confident the predictions are with respect to the score. So this mean interval score was not our invention. It was a classic method in probabilistic forecast. What we did is to modify this to adapt for deep learning. And the nice thing of MIS score as a probabilistic metric is that it does not require full predictive distribution, which is not available in deep learning, and it's rather easy to compute. Okay, so without going much into details, I just want to show you the uncertainty quantification for the COVID-19 forecast. Right, what we can see is that this is a United States forecast, and the shades represent the confidence intervals. And these are different states for Texas, for California, where I am in, and different other states. We can see that the truth is a solid line, right? And the red one represents the forecast using the quantile loss, which is the frequentist approach for uncertainty quantification. And then the red line is the SGM-CMC, which is the Bayesian approach for uncertainty quantification. And usually what we see is that the frequentist approach gives a much larger confidence intervals, whereas the Bayesian approach is more confident. It gives us a narrower intervals. But roughly, the mean of the predictions for frequentist approach is much better. It covers the truth much better. And this vertical line means the starting of the forecast. Overall, what we see is that the forecast roughly covers the truth of the black line, and then the Bayesian method gives a much more confident estimate. So this is a slightly different application, which we showed in our paper for traffic forecasting. Again, we see similar patterns where we generate accurate forecast, which follows the ground truth, but then Bayesian methods gives a much more confident estimate. Right? And that's for the second part. Any questions?
Then I have one question, quick question. So for this one, like if we want to know the uncertainty, machine learning people tend to use Gaussian processes. So compared to those methods, how this proposed method is better?
Exactly. That's an excellent question. So for forecast, right? Actually, Gaussian processes does not scale at all for this problem, because for example, the traffic example, we have about several hundred sensors. At the same time, each sensor generates about several hundred dimensions of time point, and that basically total will be like several thousands of dimensions just per one forecast. And Gaussian process is not able to generalize to scale in this case, right? Another thing is that so it doesn't give very good predictions as we show in our previous paper. Then we have a new paper that's just on arXiv. It's basically showing that Gaussian processes provide uncertainty for the forecast, but it doesn't provide the intrinsic uncertainty of the system. So the deep learning, when we build a model for deep learning, we wanted to approximate underlying dynamics, which we essentially will ask the deep learning to be the surrogate of the underlying system. So in this new paper, and I will send you the link later, what we showed is that Gaussian process is not able to capture the intrinsic uncertainty in the system, which means we cannot even use the predicted uncertainty to guide decision making. For example, we actually compare Gaussian processes versus deep uncertainty quantification in Bayesian active learning setting. What we found is that Gaussian process doesn't give accurate uncertainty, which allows us to sample for the next data point.
Nice,
yeah,
nice.
Yeah. Okay, then I guess the last part I wanted to briefly talk about is some new work that we did that I'm very excited about. This is about incorporating symmetries into deep learning as a third way to incorporate physical principles into deep learning. So there's this famous theorem by a physicist called Noether, and she said for every symmetry there is a conservation law, which means for example, the conservation of energy means the time translation invariance, and so on and so forth. So if we can somehow build symmetry into the deep learning to learn underlying dynamics, we just automatically guarantee conservation in these systems. So in machine learning, the idea of building in symmetry is broadly called the Equivariant Learning or Equivariant Network. And there was actually a tutorial at NeurIPS this year about the exact same topic. So the idea of Equivariant Learning is to learn the function f. Again, this function f is an underlying system dynamics, right? We want to learn an f function that approximates the underlying dynamics. But when we say the function is equivariant, we essentially want this function to satisfy this following equation, which means a group transformation applied to the input of the data will naturally apply to the output of the data. And I will elaborate more in the following slides. Okay, so then let's look at a very simple example of learning dynamics. Right? And actually, this is related to the question that Makoto asked in the beginning about out-of-sample distribution generalization. And this paper was published in L4DC just like yesterday. and this is about understanding the gap between physics-based model and data-driven models. Okay, so then let's look at a simple example. The underlying dynamics is a sine function. Okay, so then we basically give the deep learning model some previous timestamp of the sine function, and we ask the deep learning model to forecast the future timestamp of the function. What's different here is that this sine function is governed by a few parameters, right? We call it theta. So the parameters include the magnitude, the frequency, and the phase, which is the initial position of the sine function. And we call all this everything as theta. So on the left-hand side, what I showed is that the theta in training and testing, they fall into the same bracket, A and B. So these are in distribution generalization case. What we can see is that the deep learning model learns perfectly, right, which is in the dashed line here. It learns perfectly with the ground truth, which is not surprising. But let's look at the out of distribution generalization here. Right? So in this case, the parameter theta in the training theta TR is from the interval A and B. But the testing distribution for the parameters is actually in B and C. And we can see here that even with the most powerful deep learning model for forecasting, it does not learn the correct dynamics. So the predictions are actually quite poor compared with the ground truth. So this kind of generalization problem is actually pretty unique for dynamics learning, because typically when we say out of distribution generalization, we just meant the distribution of data is different from training to testing. But for dynamics learning, the generalization actually means the changing dynamics, because the distribution for the sine functions are roughly the same for the second case on the right-hand side, because the values of this function are roughly the same. So the training and testing are roughly the same. There's not much distributional shift in the terms of data distribution. But rather, there's changing dynamics, which means that the distribution of the parameters that govern the system are changing from testing to training to testing, and this leads to the test distributional shift, which is very difficult to learn. And this is still an open question. So the first step we take in to address this question is to leverage the idea of physics. What we think is that even though from training to testing, the parameter distribution have changed, but the law of physics does not change. So if we can incorporate the laws of physics into the machine learning model, then we will automatically allow the model to generalize. So then this is basically the idea of our Equivariant paper this year about incorporating symmetries for improved generalization. And what we want to do is to forecast the very challenging task of the turbulence, as shown on the top video. So we have the previous frame of the turbulence. We want to emulate the evolution of the turbulence with the goal to speed up climate simulations. This is done by my PhD student, Ray Wang, and postdoc Robin. Okay, so then brief introduction of symmetry. Symmetry, the key concept is group, right? A group is a set with a composition map. And this is a map to itself. So identity is the element in this group. And for this, every element in the set, small g in G, there is an inverse element, G inverse, also belong to the same group. So a familiar type of group is a rotation group in 2 dimensions, the 2D rotation, shown on the right-hand picture here. So it's easy to see that non-rotating, which is identity here, is in this group. And then if I left rotate by 60 degrees, I also have the right rotate by 60 degrees also belong to the rotation group. Okay, then what I mean by invariance or equivariance, right, is just saying that if I have a function and a group G, if a function is invariant to a group, that means if I apply group transformation, such as rotation to the input, it will not change the output of the function. And if a function is equivariant, right, that means if I apply the transformation G to the input, it will automatically apply to the output of this function. So this is very natural for generalization. It just means if I have some data set changed by a group transformation from training to testing, then if I can learn a function that is invariant or equivariant to this type of group transformation, it would automatically learn that this to apply this transformation to the test set, and therefore the model naturally generalizes to the test set within a group transformation. And let's consider a simple example. For instance, if I consider the function as a velocity field on a two-dimensional grid, and I have a space x and a velocity v, so this function scales the velocity by 2. And then let's say the group is a rotation group, and the rotation group representation in 2D is a 2 by 2 matrix of cosine by cosine signs. So if I say a group is invariant, a function is G-invariant, that just means if I follow the path by, from the top, where we first scale the velocity field by 2, so you can see that the little vector field gets scaled up by 2, and I rotate the vector field by 45 degrees, it's the same as if I rotated first by 45 degrees, following the left bottom path, and then scaled it up by 2. So then following the top right path is essentially leads to the same results as following the bottom right path, and therefore the function is G-invariant, equivariant. So if I want to learn the turbulence dynamics, we basically need to look into differential equations. So when we say differential equations have symmetry, essentially just means the solution itself have symmetry. So if I have a system which is governed by some differential operators, then I will know the solution phi is basically invariant under group transformation. So if a phi is the solution of this PDE, then G of phi is also a solution of PDE. So that's the definition of symmetry in differential equations. So now naturally we can write out all the symmetries in a Navier-Stokes equation on the second column. So Navier-Stokes equation is the governing equation of turbulence. Right now we can identify 5 different symmetries in the system. So if I want to build a neural network that can learn the symmetry, we want a neural network to be G-equivariant. In this case, we have a function which is approximated by a deep neural network. And we can really basically change the input and output representation of the function. And what we can do is change the intermediate representation or the hidden states of the neural network to make the whole thing equivariant. And in our paper, we proved that even with residual connections, as long as we make every layer to be equivariant, then the entire network is equivariant. Adding skip connections does not change this equivariance. Okay, then how can we implement the symmetry in deep learning? The idea really derives from, the common ideas behind deep learning, which is through weight sharing. We know that convolutional neural networks are translation invariant. It achieves so by sharing weights across different filters. So a more general case of that is the G-equivariant convolutional architecture derived by Weiler and Sesa. And this is saying that if I want a convolutional layer to be equivariant with any group, then this kernel needs to satisfy the group invariance under conjugation. So it means I have a kernel K. If I left multiply and right multiply by the same group, but possibly different representation, then this kernel satisfies the symmetry we want. So then in our paper, we derive the different type of kernels in convolutional architecture, such as rotation, uniform motion, scale, and etc. Let me just show you the results since we're running out of time. Basically, if I, just answering Makoto's question, if I have a test set that is very different from the training set, in a different dynamics, how can I make the model to generalize better? And that's basically answered in this case by equivariant net within a group transformation. So I have a target, which is a ground truth, and then the non-equivariant model is our baseline. So this model does not know about the symmetry in the system. So when we basically rotate the test data by a certain degree to a non-equivariant model, the distribution of data will be completely different. And therefore, it does not know how to generalize. But for equivariant models, because it has built-in symmetry, it naturally learns to generalize, Right? Let me play the video for you. You can see that the prediction from the equivariant model follows the ground truth quite perfectly, whereas the non-equivariant model fails completely in this case. Similar example can be seen for uniform motion and scale. And of course, the limitation for this work is that it only allows the model to generalize within the group transformation. When in certain times, the change in the test from the training might not perfectly follow a certain group transformation or even doesn't have a group. So we have a new paper which describes this kind of situation, but I probably won't have time to talk about this today. Okay, then if we look at experiments on the ocean current forecasting, and this is to forecast the future velocity field of ocean currents, we can see that the root mean square error over different upscale of the test set. So we scale up the turbulence in the ocean by different factors. We can see that the equivariant models is very robust against this kind of change in test distribution. And the red plot shows a physics-based metric called energy spectra. Okay, then I guess we'll quickly just conclude. We probably no have time to talk about this. Let me conclude. Okay, so basically, I talked about different ways to incorporate physical principles into deep dynamics model because deep dynamics model, dynamics modeling or spatial temporal dynamics learning are fundamentally connected with physics-based modeling. So I talked about 3 different approaches. Residual learning, which is learn the correction term of the physics-based model, but sometimes we need to be careful because learning-based model can be too flexible. So we have to incorporate such as spectral normalization to regularize the behavior of learning-based methods. Talked about trainable operator, which is to replace the mathematical operators with the trainable weights. And I talked about the example of COVID-19, where we replace the diffusion operator with trainable weights. Leads to diffusion convolutional neural network. And I talk about equivariant learning, which is a way to incorporate symmetries into deep learning to guarantee laws of conservation, but more importantly, to improve generalization for a very different type of dynamics. For future work, we're very interested in stochastic dynamics, and we're also interested in multi-agent interactions, even with external inputs, such as in a reinforcement learning setting. Okay, and you can check out the code and the paper on my personal website. This contains all the papers I talked about today and the code and data. And or follow me on Twitter, where I occasionally publish the written news in a group. And here are the funding agencies for this paper. Finally, I want to share this quote to everybody from Albert Einstein. He said, "Time and space are not conditions of existence. Time and space is a model of thinking." So hopefully after my talk today, I can get you to think a little bit in a mode of space and time. And feel free to email me if you have any questions. Thank you.
Thanks for the great talk.
Thank you.
It's very interesting. So actually, there's some questions in the chat box. Could you please respond?
Yeah, let's see. GNNs can be used to DNNs can be used for dynamics with many parameters. How is vary from your deep learning model? Yeah, so our paper actually was one of the first papers to learn graph, basic GNN. So if we put this diffusion convolution in a kind of static setting, it just reduces to the standard GNNs, right? Then we put this GNN into integrate this GNN or diffusion convolution operator into sequence modeling approaches. So that leads to diffusion convolutional RNN. Which is our invention. And it was one of the early papers about modeling kind of dynamic graphs, but fixed graph, but evolving dynamics on the graph. Does that answer your question?
So did you answer the is NT-G invariant? Okay.
Isn't G invariant f of so it's maybe there was a typo, but I think the G invariant is a special case of equivariance, right? Because we can just make the group as to map itself.
Okay. Okay, so do you have, from the audience, do you have any further questions? If you have any questions, you can type on the chat box. Or you can directly ask a question from the Zoom, whichever is fine. Okay. Yeah, so then I think there's no further question. So if you have any further question, please contact the roles directly. And also, it was really, really nice talk. Thanks again for your presentation. I'm really interested in your talk. So let's
Thank you
thank
so
the speaker
much.
again.
Thank you. Thank you for the great questions.